In this video, we're going to look at some basic probability rules. And the first thing I want to do here is, let's say in my class, I have, we'll say maybe 18 girls, and we'll say, let's just say 12 boys. Something like this. And I'm going to randomly select a student. And I want to find what's the probability that the student that I select is a boy. Okay, so to find this probability, what you got to do is you got to find the total number of outcomes in the sample space. And so in this case, the total number of outcomes, you have to add the two together. And you would actually get 30 outcomes in the sample space. Okay, and then the top number would be the number of boys, 12. And this would give you the total, or this would give you the probability of randomly selecting a boy. And it looks like it's like 0.4, 40% chance of selecting a boy. Okay, so the reason for showing this is a probability problem is not always the small number divided by the large number. Okay, you got to be careful. So it's always the number of outcomes in your event divided by the total number of outcomes in the sample space. And so sometimes you have to add them together to get the total number in the sample space. Okay, sometimes you could have more than two categories. You might have 3 or 4 categories, and in that case you would add them all together, and then you would find however many outcomes are in the event over the total. But the point here is you would have to total them all up to find the total. Okay, so now I want to talk about the complement rule. This is a very important rule that can be used in a lot of different ways, and we're going to use it throughout this class. You'll get very familiar with this. But let me tell you first what complementary events are. Okay, so a complementary event is when you perform the experiment, 2 events are complementary if when you perform it, either one or the other occurs. Those are like the only 2 possibilities. So it could be like rolling an even number, rolling an odd number on the dice. Those are complementary events because it has to be one of the 2. Drawing, or like in this example up here, randomly selecting a boy or randomly selecting a girl. Those are complementary events. You could have one that maybe a part is defective, like maybe parts coming off the assembly line, or the part works fine, right? So when it comes off the line, it's either a defective or it works. Those are complementary events. Okay, and so oftentimes you're dealing with 2 complementary events. And so for the sake of notation, you can call either event E. Okay, and then the other event would be not E, because if when you perform the experiment one or the other has to occur, then either E is going to occur or E is not going to occur, in which case the other one occurs, right? So in this case, like defective, that would be E. Not E would be that it works, right? But I could have said works is E, and then not E would be that it's defective. It does not work. Okay, so on. So the reason for using this notation then is that we have this rule, and this is called the complement rule. The complement rule, okay? And the complement rule just says the probability of the complement of an event is just equal to 1 minus the probability of the event. Okay? And the main point is, if you have 2 complementary events, if you know the probability of one, then you always know the probability of the other. Okay? Because the probability of the other is 1 minus the one that you know. Okay? Another way you can think about it is if you add the two together, they're going to add up to 1 because those are the two possibilities. And so since they add up together to be 1, then if you know one of them, you can take 1 minus the other to get, you can take 1 minus the one you know to get the one you don't know. Okay? Maybe even an easier way of thinking about it is something like if 10% of the parts work, 90% do not work. 90% would not work, right? Or if 75% of them work, 25% do not work. Okay, they add up to 100%. And this is the same idea, but instead of 100%, you're using 1, and 1 is the same as 100%. So let me just give an example. So let's say the probability that a part is defective, we'll say is like 0.0137 or something like that, right? So then the probability that it works here, these are complementary events, it'll just be 1 minus the probability that it's defective. And so I could do 1 minus 0.0137. And I get like 0.9863. So very good chance it's going to work. Small chance that it's not going to work. Very good chance that it is going to work. And these two actually add together to be 1. Okay? Or if I thought of them in terms of percent, this would be 1.37%. Right? And this one would be 98.63%. And if you added those together, you'd get 100%. Okay? So that's the complement rule. That's one of the important basic rules of probability. Okay? So then there's also something called and or probabilities. Okay? And I'm just going to illustrate this with a couple examples. I could have the probability of drawing an ace and a heart. Okay? Or I could do the probability of drawing an ace or a heart. And these two are different things, okay? So the idea here is I'm randomly selecting one card, okay? And let's say that too. Randomly select one card from a deck. Okay? And if I want to find the probability of drawing an ace and a heart, what that means is that the card I draw has to be both of these. It has to be both an ace and a heart. Okay? So when you draw a card from a deck, there's 52 outcomes. So you have 52 on the bottom. And now my event is ace and heart. So that one card I draw has to be an ace and a heart. It has to be both. So how many cards are like that? There's only one. And that is the ace of hearts, right? So what this means is the card that I draw has to be the ace of hearts. It's an ace and a heart. So the probability here then is, in this case, 0.0192 if I round to 4 decimal places. So that would be the probability of drawing an ace and a heart. So now this would be the probability of drawing an ace or a heart. Okay? So this means it doesn't have to be both. It only has to be one or the other. Okay? Now, the way we use or in English is an exclusive or. It's kind of like you have to, either you're on my side or you're on their side, but you got to choose. You can't be both, right? But that's not the way it's used in mathematics. The way or is used is you don't have to be both. And is you have to be both. But when it's or, you don't have to be both. You just have to be at least one of the two is fine. If you're both, that's good too. That's okay too. You're kind of double good because you got both of them. But the point is you don't have to have both. You only have to be one or the other. Okay? So to find this probability, the bottom number again is 52. Now I got to think how many of those are an ace or a heart or possibly both. So here's how I like to do these. There's 4 aces, so I put 4 there. And I know that there's 13 hearts. Okay? Now if I add these together, I would get 17. Okay? But this is not 17 up here. And the reason for that is because when you add 4 and 13 together, you're adding the ace of hearts twice. Because there's an ace of hearts in here, but there's also an ace of hearts amongst these 13 cards. So by adding those two together, you're going to get an extra ace of hearts over here. So what you do is you add those two together, okay, but then you have to take out any extra ones after adding those two together. So there's 17, but the ace of hearts appears in both, so this would be 16 out of 52. And that's how you get that. So this would be 16 divided by 52. And I get approximately 0.3077 if I round to 4 decimal places. Okay? Ace and a heart, ace or a heart. So that's the idea behind and or probabilities. When you see that word in a probability problem, it means something. Okay? And you have to take that into account. Okay, so now there's one last thing I want to look at here, and that's this. So let's say a survey of households is taken. Okay, so let's say a number of households are surveyed. And let's say they're asked how many TVs they have. So we got like number of TVs. And this would be like the frequency. Okay, so in other words, these would be let's say the possible values for how many TVs they had. So let's say there was one household that had no TVs. We'll say 8 households had 1. 12 households had 2. Let's say 5 households had 3, and then we'll say there were 3 households with 4. Let's say no households had 5, and then 1 household had 6. Okay? And so basically this is a frequency distribution. Okay? And what we could do is we could say randomly select a household. And now we could ask some questions then. We might want to know what's the probability that the household had 2 TVs. Okay? How are we going to find this probability? Okay, so I know that 12 households had 2 TVs. Okay, so what do I need? I first need the bottom number. How can I find that? Okay, so think of it like this. Think of you're taking your sample and you're writing down the Smiths. They have 2 TVs and you put it in a hat. The Joneses, they have 3 TVs. The Thompsons, they have 1 TV. And you're putting all these names in a hat and then you're drawing a name out of the hat. So you got to know how many names there are in the hat. And to find that, you actually add up the frequencies. That gives you the total number of households. So when you add this up, that's equal to 30. I think 20, and yes, it's equal to 30. So the bottom number is 30, right? And then I want to know the probability that they have 2 TVs. Okay, well, there's 12 households that had 2 TVs. So the top number is 12. That's the number of outcomes in my event. Okay, so I could do 12 divided by 30. And I get 0.4. Okay, in that case. Let's see. I could do... I could ask other things. What's the probability that they have 5 TVs? Okay, well, still 30 households. And then I got to go to my table and I got to see how many have 5 TVs, and none of them do. So I got 0 out of 30, and I get a probability of 0. In other words, that's an impossible event. And that makes sense because none of the names in the hat are going to say 5 TVs because none of the households had 5 TVs. Okay, let's do one more. What if I say probability that they have at least 4 TVs? At least 4. What does that mean? At least 4. So it means that they have 4, 5, or 6. They have 4 or more. Or the number of TVs they have is greater than or equal to 4. Well, in this case, there's only 4 people that have, I'm adding the 3, the 0, and the 1. And so there would be 4 out of the 30 people that have at least 4 TVs. And I would get 4 divided by 30. It's like approximately 0.1333. Okay? And that would be the probability that they have at least 4. So what you see is that these frequency distribution tables can lead to pretty good probability problems. And the way that you do the problem is you add up the frequency to get the total number of outcomes. And then the top number is going to come from your table, and you take whichever number of outcomes here you need for the event that you're finding the probability of. Okay? And so that's another good technique. So in the next video, I'm going to give you a chance to do some of these problems.